So we've talked about the idea of standard enthalpies of formation in the previous video, and in this one we're going to look at how do you actually apply that, and why do we bother defining this in the first place and then using it. Why do we make this is something you can look up in the back of your textbook in the appendix, for example, or there are whole books that chemists have made that include lots of different values of enthalpies of formation. But why? Now, the point of it is that we can use those enthalpies of formation to find the enthalpies of any arbitrary reaction that we want. Let's look at this reaction, for example. We have glucose reacting with water to form hydrogen, carbon dioxide, and methane. And maybe this isn't a very feasible reaction, but you're interested, what would the enthalpy of this reaction be? And so what we're going to calculate is what's called a standard enthalpy of reaction. This is going to be the enthalpy of the reaction under the standard conditions we've specified, right? Again, this degree sign means 1 bar pressure and usually 25 degrees Celsius. Okay, so there is an equation that we can use that uses standard enthalpies of formation to get the enthalpy of the reaction. So the generic form of this equation is that our standard enthalpy of reaction is equal to the sum, that's what this big sigma means, over all of our products, and we take the stoichiometric coefficients, so these n's, these are the coefficients, multiply those stoichiometric coefficients times the enthalpy of formation, standard enthalpy of formation of the products, and we subtract the same thing but with the reactants. Okay, so let's just break down this equation by doing an example. I think is the simplest way. So we add up all the standard enthalpies of formation of the products multiplied by their stoichiometric coefficients, and then subtract what were the standard enthalpies of the reactants multiplied by their stoichiometric coefficients. So let's do that with this example here. So for this sum here, we're going to need to do all of our products here. And for this sum here, we're going to need to do our reactants over here. And we'll need to look up these enthalpies of formation. So I've got a table here where you can look these up. I'm going to be looking at table 6.2 in your textbook. There's also a table in the back of your book that has more values. So that's where these values are going to come from that I'm going to use. So delta H for this reaction is going to be equal to, we're going to do the products first. So we're going to need 4 times the enthalpy formation of H2 gas, 4 times CO2 gas, and 4 times methane gas. Now, one thing we can point out is that H2 is in its elemental form. It's in its standard state under standard conditions. So this will have an enthalpy of formation of 0. We'll include it just for completeness sake, but it's going to be 0. So we have 4 times 0 kilojoules per mole. So that's our H2. We're going to put this all in parentheses so we don't get our signs mixed up. We add that to our enthalpy of formation for CO2. So 4 times, if we look that up, it's negative 393.5 kilojoules per mole. And for our purposes right now, I'm just going to keep track of these up here. So this is the 4 CO2, this is the 4 H2 gas, plus 2 times negative 74.8 kilojoules per mole. And this is our 2 methane. Okay, so we take all those, add them together, and then we're going to subtract our reactants, which is 1 times negative 1,274.4 kilojoules per mole. That value, again, all these values are coming from the table, and this is our C6H12O6 solid. Again, our stoichiometric coefficient is 1 there. And then we add in our other reactant, which is 2 times negative 285.8 kilojoules per mole. This is our 2H2O liquid. Okay. So once we do all that, we plug it into the calculator. All right, and I'll go ahead and do that myself right now. So move my calculator down over here so I can see everything. So we have, I'm going to use my parentheses, 4 times 0 plus 4 times negative 393.5 plus 2 times negative 74.8. Subtract, after closing the parentheses, again with an open parentheses again, negative 1274 plus 2 times negative 285.8. And all of that, make sure I added all this together correctly. 4 times 0 plus 4 times negative 493.5 plus 2 times, oh, that is my problem, 74.8. All right. And we get positive 122. And that is our, again, what are we after? This is our standard enthalpy of reaction for this reaction. Okay, so we find out that this is an endothermic reaction, and it's endothermic by a specific amount, 122 kilojoules. And this, I'm not putting a per mole value because this is specifically for this equation as balanced, right? So balanced like this. So it's for 1 mole of glucose or 2 moles of water or 4 moles of hydrogen, et cetera, et cetera. So these are very similar to the enthalpies that we've seen for other reactions. This is just, the only difference here is that this is under standard conditions specifically. And some of the other ones we looked at may or may not be under standard conditions. Now, I mentioned that this is an application of Hess's law, and I just want to illustrate why that is. Essentially what we're doing is we're creating a bunch of enthalpy value and a bunch of reactions that we're adding together to get our enthalpy values. So I'm going to sort of depict this graphically. So we're starting with our C6H12O6 and our water. It was 2 moles of water, right? Yeah, 2 moles of water. We're going to sort of depict that as being at a specific amount of enthalpy here, right? So if we're looking at H in this direction. So that's our starting point. And what we're doing is we are converting all of this, maybe go even higher, into the elemental forms. Theoretically, we're not actually doing this, but in what we're doing in this process of using the enthalpies of formation, we're just saying, okay, we're going to deconstruct this down to 6 carbon, 12 plus 4 is 16 hydrogen, so that'll be 8 H2 gas molecules, and then we need 8 oxygen total, so 4 O2. We're sort of deconstructing all of the elements here into their elemental forms, and this is, this is our 0 point. So we're taking whatever that is, and then what we're doing is recombining them into our products. In this case, I'm drawing it as positive because I know this is our net change overall is positive 122. So when we go from here to here, we know the final result is what we just calculated, positive 122 kilojoules. And we're forming our products out of these elements. Again, our products being, let me just look over here, our products being hydrogen gas. So the hydrogen stayed the same, but also, and let me get the right coefficients, 4H2, 4 CO2, and 2 CH4. And so we're effectively taking these steps. These are not the actual steps that happen in the reaction. It doesn't completely decompose into all of its elements, but we're sort of taking, we are taking those reactions as our reference point. So we're referencing the reactants to the elements, and we're referencing the products to the elemental forms, and then we can use that to get the overall positive 122 kilojoules for this example. If that's a little confusing, this is just sort of what's happening behind the scenes. All you really need to remember to actually do problems related to this or to calculate is this equation up here. for your enthalpy of reaction, if you want to use the enthalpies of formation, you add up the enthalpies of formation of all the products times the coefficients associated with them, and then subtract the sum of all the enthalpies of the reactants multiplied by their coefficients. So that concludes our chapter on thermal chemistry, and that concludes one of the most useful properties of enthalpies, and taking advantage of the fact that it's a state function, we can come up with whatever path we want to get from point A to point B. We use the path that goes through the elements, and that lets us use the standard enthalpies formation to calculate any reaction we'd like that involves anything we already have in our table of enthalpies of formation.